Transverse wave is a wave that vibrates perpendicular to the direction it's traveling in a sine curve shape. So what that means, let's look at the wave to the right. It's moving to the right. We can observe that because the wavelength is moving to the right. However, the direction the wave is traveling, in this case it's oscillating up and down, makes a 90-degree angle with the vector for its direction. Light and water waves travel as transverse waves. To understand transverse waves, we need to understand some of the vocabulary, and then we need to be able to identify that vocabulary within a sound wave or within a transverse wave. Equilibrium is the midline of the wave. This is the medium of the wave's resting position. Imagine a string. If you could make a string into a wave by shaking it up and down. If the string is just laying there or pulled straight, that's the equilibrium. It's its resting position. The wave isn't up, the wave isn't down, it's just in the center. The crest is the highest point on a wave. The opposite of the crest is the trough. The trough is the lowest point on a wave. Both the crest and the trough are going to be equal distant from the equilibrium line. The wavelength is the distance between successive crests of a wave. You could also look from crest to crest, trough to trough, or node to node. A node is where it crosses the equilibrium line. The amplitude of a wave is the distance between a crest or trough and the equilibrium line. This is based on the amount of energy in the wave. The more energy, the bigger amplitude. So if I put a lot of energy in, my crests are going to be really high, my troughs are going to be really low. If I put a little energy in, the crests are going to be kind of high, but not very. The troughs are going to be kind of low, but not very. Let's apply these terms to a model or a drawing of a transverse wave. So in this case, we have a piece of string tied off to a rope. If you oscillate or shake it back and forth, or up and down in this case, it's going to create a transverse wave. We can observe this in sound, light, and in this case, a mechanical wave. If I pulled that string straight, had its resting position, that's what we would call the equilibrium line. This is the resting position for the medium, so this is a flat surface of a lake before you throw a rock in. This is the motion of the air in a quiet room. The crests are the highest points. You can think of them as peaks and valleys. Crests are the peaks, troughs are the valleys. Assuming the same amount of energy is put in, the amplitude, which is the distance from the equilibrium line to a crest or to a trough, will always be the same. Crests are the same height away from the equilibrium line that troughs are from the equilibrium line. The bigger this amplitude, the more energy in the wave. The wavelength can be measured by looking crest to crest. We usually describe it as crest to crest because it's the most observable. However, you can pick any point on that wave and find where it repeats again. You could go trough to trough. You could go node to node. A node is where it crosses, or where the waveform crosses that equilibrium line. These are all defined points. That's why we use either crest to crest, trough to trough, or node to node to calculate the wavelength. Let's count waves. So we have here an example of a wave. It's a transverse wave. Traditionally, I would count crest to crest. So there's one part of the wave, crest to crest. That's one wavelength. So I have 1, 2, 3.5 waves. Another way to observe this is each one of these examples has a trough, and on either end of it, it makes up a crest, as 2 halves of a crest. So we have a crest and a trough, a crest and a trough, a crest and a trough. This has half a crest, half a trough, so it's only half a wave. We could also go trough to trough, trough to trough, trough to trough, trough to trough. That's still 3 full waves and a half wave. They each have a full crest and two halves of a trough. So that's a full crest, a full trough. That little half wave on the left has half a crest, half a trough, so it's only half a wave. We can also go node to node. This example really highlights that idea that a wave has both a crest and a trough. So node to node, node to node, node to node. On the far left side, I'm left with half a crest. On the far right side, I'm left with half a trough. So I have 3 full waves and 1 half wave. Either way, 3.5 waves. I know that I'm looking at those nodes because that's where the equilibrium line and the wave cross. Another common wave is a longitudinal wave. These are also known as compressional waves because as you observe, what we're doing is compressing the medium, passing through different periods of compressed and uncompressed. A longitudinal wave is a wave vibrating in the same direction it's traveling. Notice the waves are moving forward. The object that's creating this longitudinal wave is also moving in the same direction. It's oscillating back and forth, creating compressions. Sound waves travel in this same pattern. Longitudinal waves are slightly less complex when we describe them. There are 2 different areas on a longitudinal wave. There's compressions. This is a region in a longitudinal wave where the particles are closest together. This was those darker lines where those particles had been compressed. There's rarefactions. Be careful saying it. It's not rare fractions, it's rarefaction. It's a region in a longitudinal wave where the particles are furthest apart. The wavelength is the distance between the 2 consecutive compressions or 2 consecutive rarefactions. When we look at a longitudinal or compression wave, we can see there are compressions, areas where in this case the spring is closer together. There are rarefactions, areas where the spring is further apart. The distance between the beginning of a rarefaction and the beginning of the next rarefaction would be a wavelength. Likewise, the beginning of a compression and the beginning of the next compression would be the wavelength as well. In this example, I know I have a longitudinal wave because not only can I see my compressions and rarefactions, but I can also see that the wave will be moving horizontally and the hand is moving the spring horizontally. They're moving in the same direction.